Yeah, thank you for your patience. We will start now. This workshop is conducted by Rbcdsi. So, this they are the Robert Bosch Center of Data Science and AI. Center was started to expand AI adoption in engineering application and leverage the available expertise on network systems, modeling across various institute departments. In the last 5 years, we have grown to be the preeminent interdisciplinary research center for data science and AI in India. We now have one of the country's largest groups in network analytics and deep reinforcement learning. We also have one of the most active natural language processing and deep learning groups. We publish extensively in conferences and journals and have received numerous best paper recognitions. Uh, from uh, Here we have our first speaker, Mr. Dr. Nirav P. Bhatt is an assistant professor at IIT Madras only, and he is also a faculty member of the RBCDSI. He earned his bachelor in chemical engineering from the MS University of Baroda, masters in chemical engineering from IIT Madras, and doctor's science from EPFL Switzerland. Currently, he is assistant professor with biotech department in IIT Madras. His research interests include modeling and identification of biological and chemical systems, and machine learning and data analysis of engineering and financial systems. I want to bring him to the stage. Please.
Okay, yeah, good. We're well to go. Yeah, thank you everyone for coming on the Saturday morning to listen to me. I hope that I will make it worth. As I already introduced that I am a faculty with Department of Biotechnology and also part of several centers, particularly Robert Bosch Center for Data Science in AI, which is an umbrella center for some of the centers I have mentioned. So what I'm going to do is I'm going to talk briefly about role of AI in drug discovery. Particularly, I will look at one of the methods called graph neural networks. And I'm trying to keep it more generic talk to motivate you to take this subject as you go along, because I don't know the composition of this particular audience. So there might be some technical terms, and I'll try to avoid the equations. One or two are there. But I'll start with some chemistry. So this is some structures. You must have seen it sometime in your chemistry class or somewhere when you try to go to the references. Do you know what they are? They are some of the antibiotics which we discovered in last 20 years or derivatives of them. And antibiotics plays an important role in our lives, even you believe or not, because we take antibiotics left, right, and center. And in last 200 years, antibiotics is one of the reasons we can actually manage to escape death very easily. Like 200 years ago, people get the common infection and they die. Okay? Now we can actually treat common infections like what the doctor call it textbook way. Doctor will know without thinking they will give you medicines, because it is so normal for them to give those medicines. And how to discover this medicine is a question in place. So people are actually working very hard to come up with newer antibiotics. And last 30 odd years, we have not made much progress to come up with the new antibiotics. One of the main reasons is that it's not easy to generate the antibiotics. Until 2020, a set of faculty from different aspects of life, Collins, these all are from the Harvard and MIT. Some of them are actually pure chemists, some of them are computer scientists, came together and created and discovered a new antibiotics from the set of antibiotics available to them using the deep learning. Specifically, graph neural networks they used, which has become a main neck in terms of speeding up the process and come up with a helicine, which is a new antibiotic or has a property of antibiotics. Of course, it has long way to go to come to the market. This, I think it is already in market, the way I understood, but for a particular purpose. And the idea here is not to show that we have a new antibiotics. Idea here is that we have a capability with a lower cost to figure it out new antibiotics. Why? Because if you have read that antimicrobial resistance is happening in the environment, and the existing antibiotic may not work. Sometimes if you go to a doctor, give you antibiotics, after 3-day course they say, okay, you are not well, I'll give you higher order of antibiotics. Right? The reason is that over the time the bugs are getting smarter and smarter, and I think COVID has actually shown us how faster they can become smarter in terms of variants, correct? One variant comes after another variant. And we do not want to die of some simple infection, right? That's mankind has achieved that a long time ago, and we want to do that, and that's why creating a new antibiotics is becoming a new challenge, because superbugs are coming up, and we want to ensure that we can actually treat those superbugs in a timely manner. And that's why the role of AI comes into play. Can we actually speed up this work? So let me go to some motivation to you why AI can help. So typically before AI, this is the way people actually discover the drugs. People work hard to discover the drugs, and that's why they are costly sometimes, and you will see why. So these are the 5,000 to 10,000 compounds which have a possibility to be a drug, are screened through experiments, some computational chemistry, calculations. And at the end, after a couple of years research, only 5 compounds will go to the clinical trials. Clinical trials means they will be tried with the human being and see whether they have some efficacy in the human being. There are preclinical trials with the mouse and animal trials and etc. after that. Preclinical trials requires a lot of safety, durations and etc. And again, after those 5 compounds, only one will become a new drug, what we call blockbusters in the pharmaceutical industries. And this process takes a lot of time and also money. So sometimes you wonder why some drugs are costly, because there are not many patients for that drug, but to discover the drugs you have to spend billions of dollars. Right? So that's why some of these drugs are costly, and what we are trying to see is that can we use computational approaches which can help us to reduce the cost of discovery at different stages. It can be staged at the drug discovery itself, where we try to screen simultaneously thousands of compounds, or at the 5 compounds level where we analyze the data quickly and say that no, out of these 5, 2 are not going to work with the preliminary data with the confidence, and move on with some of the compounds which are promising. It also improves the pace of discovery and development, because development is beyond discovery. We have to go and actually produce them. Can we actually use AI to do that? And lately, AI has been used for many of these tasks, like toxicity detection, which is an important aspect of the for drug discovery, protein binding affinity predictions, molecular water solubility predictions, drug side effect predictions. Often you have a complex disease and you need multiple treatments, or even simple, like some people are having a diabetes and cardiovascular disease, then doctor has to be very careful to give medicines. So in those cases, you have to understand whether if I give 2 drugs, what kind of side effect they will give, or even single drugs, what kind of side effect will give. So this is some of the motivation for why we need drug discovery. Now the question is, what is drug? Drug is a simple or sometimes complex chemical molecule, which many of us might hate during our chemistry days, but that it is. You have to actually embrace it, because the life is all about chemistry. So molecule you can see sometime in this form, sometime you can see in this form, but beyond that we have not seen. but the chemist also represent it in this form called smile strings. It is a linear representation of the 2D structures we often see in the chemistry book in high school. People actually take these structures and create something called graph models. I'll talk about what is a graph in some time. But what they do is they try to actually create some picture which actually allows them to represent any molecule. People use some kind of molecular fingerprinting based on certain criteria, whether certain molecules are there, certain molecules are not there, etc. Another way people actually use is called descriptors. Describe the drugs. What is the molecular weight? What is the solubility in water, etc. And all these properties are used typically to understand the other property of interest, because this is the easier to get. Let me check. These are the properties which are relatively easier to compute. Another question is how to synthesize new molecule rapidly. ChatGPT will give you a molecule, but somewhere you have to synthesize, because molecule is a physical quantity. How you can synthesize from the existing molecules is again a big challenge in the industry. And the last question is personalized medicine. Well, will this molecule be effective for a particular individual? It might be effective for a set of population, but not to individual, and can we provide a personalized medicine? And the lucrative side, of course, there are a lot of startups which coming up in AI in drug discovery. I think it is 2020 news where $2 billion has been raised by AI startups. Google has a startup also, Alphabet has a startup also, and this business is going to grow by $9 to $10 billion in terms of revenue by 2030 by some of the reports. And the question is, can we actually, this is money which is nowadays everyone likes it to do that, but more important question is, can we use AI to bring affordable drugs for all? Because drugs is still not affordable to many. Often when you use YouTube and you see there is an ad talking about child requires drug worth of crores, because those drugs are not useful to produce for many pharmaceutical industries, because they cannot do for mass. It is rare what we call orphan diseases. For orphan diseases, people would not like to spend a lot of money in the research, but can we use AI to actually make sure that they are affordable? And with that, I would like to thank you, and as well as if you have any questions, you can ask me right now or afterward. Thank you. Yeah, sure. So I can give you my email address. Just to tell you, most of this material is available as a part of online BSc course in one of the special elective called Big Data in Networks Biology. I'm getting the name correct. Yeah. So it is available. It is some of the last lectures. We talk about methods and the applications. So it is available. It might be a little more technically involved, but you can go through the lectures, and or even you can take that course as in the future. Yeah. Yes. Yeah. Right. Thank you. Anybody else?
Could you name any drug which is already in the market, developed using these deep learning, machine learning methods, or how close is the industry to the first ever deep learning?
So I think Helsin is available, frankly speaking, because it is one of the existing drugs. Whether they are using for that purpose or not, I don't know. The FDA approved or that is not known. Because FDA approval requires time, but there are repurposed drugs are there. I think I forgot the name because I'm not good with name, but there are repurposed drugs I know that which people have used for one disease. I think some version of Viagra people are now using for cardiovascular diseases. Yeah. So that is there. That's FDA approved. So repurpose is there, but completely new drugs, I'm not sure it's still there or not. Because as I told you, FDA takes time to approve it. I just wanted to show one thing. But some of these drugs are, the Helsin is one of the known drug, but it is now useful for other purposes. So this is definitely available in market. Whether people prescribe it or not, or FDA allows them to prescribe, that's a different story. But this is available in market. Yeah. Yes.
This technique is reducing the time for identifying the lead compound or the trial period.
Identifying the lead compound, I would say, rather than trial period. Trial you cannot, that's experimental.
Okay.
You can do some feedback to improve it. Like I think one of the slide here is very interesting where they talk about, okay, here they did not talk about it, but you can actually go feedback at some point of time from validation to improvement, but which is what I call incremental improvement, and you can decrease the time of actually validation because you only take one or two lead compound, decrease it and then use it, but I don't think so. Without that, you can decrease the validation.
So when you are training the model for the side effects, for predicting the side effects, can't that same technique be used for trial period?
In principle, yes, but you still have to do experiments. No?
Okay.
See, the problem is that you have to do some experiments. So I would not like to say that it is really going to reduce it. Maybe cost will be reduced because you will do lesser trials. Because certain experiment has to go for certain time, okay, as per the experimental protocol. That I can't reduce it except I come up with some new protocols.
Okay.
So that is not I am considering application of AI right now in drug discovery. There are people trying to do that, but best of my knowledge, it's people have not come up with the experimental protocol itself, which using AI which reduce it. It's still a chemistry domain, but you can actually do iteratively. You choose less leads, reduce the cost, and go back and do that.
Okay, thank you.
First, this one, which one? The slides I can make you available. Not when nothing is my. It's so I can you can. My you want my okay.
Hello, thank you, Nirav sir, for your time here and the great immense knowledge about how we can use AI and deep learning in for a drug discovery or anything related drug research. That was a great knowledge, and as a part of from NPTEL team, we will like you to give a gift from our side. Uh, Thank you for your time, sir. Okay. Hello. Hello, everyone. So now we have Dr. Gugentope, is an assistant professor at Department of Computer Science and Automation in Indian Institute of Science. He is also an associate researcher at the Robert Bosch Center, IIT Madras. His MS and PhD are from TIFR Mumbai, India. He has also done 2 postdocs, one at Technion, Israel, and the other at Duke University, USA. His work has been recognized with the Pratiksha Trust Young Investigator Award, the TIFI Award for Best PhD Thesis, and 2 IIBM PhD Fellowship. He is also the winner of the IISc Award for Excellence in Teaching. His research interest includes stochastic approximation and random topology, and their application to reinforcement learning and data analysis. So he is now available on online, and he will present his thoughts about his research and his topic. So I want to bring him. Please, Gugan sir, on you can talk now.
Yeah, can you hear me?
Yes, yes, sir. Everybody can hear you.
All right. So for some reason I'm not able to see you all, so I don't know who is in the audience and how you are reacting to presentation. So I have been given 30 minutes and I'll try to go as slowly as possible. If you have short questions, maybe one of you can ask me directly what the question is from the audience side, and I'm also happy to take some more detailed questions at the end of this talk. All right, so with this, maybe we are ready to go. So my talk today is titled Estimating Change Rates of a Web Page and Online Learning with Stochastic Approximation. So as Manoj pointed out, one of my research interests is stochastic approximation and its applications to various domains. And in this talk, I'll try to give a very ground level introduction to stochastic approximation from the point of view of an application in the context of web crawling. All right. So let's begin with some background. So the internet is a very complex entity. It has multiple web pages, and these web pages keep evolving. And it is not difficult to understand or realize that different web pages evolve at different rates, right? Like for example, if you want to have an example of a web page that evolves very quickly, you may want to consider the example of a web page that discusses the stock markets or something related to sports. On the other hand, there are also web pages which evolve very slowly. For example, web pages related to government policies, or for that matter, even web pages that discuss the institute rules, like that of IIT Madras, right? So even in such a complicated scenario where web pages keep evolving, the users expect the search engines to provide accurate information instantaneously, right? So this is a very challenging task, and users are oblivious to the underlying challenges, and they expect the search engine to provide accurate information almost as soon as you press in the query. So the search engine has deals with this in the following manner. It doesn't go about searching for the information when you put in the query. Instead, what it does is it maintains local copies of web pages, right? And whenever a user puts in a query, it only searches from this local database. Okay, so that's the key thing to keep in mind. Just to repeat, the search engine doesn't go out searching for the information when you put in a query. Instead, it has a local database of the different web pages on the internet, and whenever a user puts in a query, the search engine only searches from the local database and provides the information. So how does this search engine maintain a web crawler, right? Or how does this let me repeat. So how does this search engine maintain this local database? Okay, so it makes use of a web crawler to periodically update this local database. In particular, this web crawler is an internet bot, okay, which is deployed by a search engine to periodically visit different pages and get their latest content, right? So ideally, we would like this web crawler to update the local copy of a web page as soon as the web page changes on the internet, right? However, in reality, we have some bandwidth constraints because of which a web page cannot be updated. The local copy of the web page cannot be updated as soon as the web page changes on the server end, right? So this gives rise to an optimization problem of the following kind. We would like to maximize the freshness of the local database such that the crawling frequencies, or the frequencies with which different web pages are to be crawled, right, they are within the prescribed bounds, right? So this problem is a very important problem in the context of web crawling, and several algorithms exist to resolve this optimization problem. However, if you go and look at these papers, you will notice that these existing algorithms either presume the knowledge of the exact page change rate, that is the rate at which these web pages change, or they use some offline estimation algorithm such as the MLE, right? So in this work, and in particular during this talk, we will sort of discuss an online approach, okay, as against an offline approach. We will discuss an online approach for estimating the page change rate. Okay, so let me repeat. The job of a web crawler is to periodically crawl different web pages to get the latest content, right? So since some pages are changing very quickly and some pages are changing very slowly, and since we also have some constraint on the bandwidth, right, or how frequently the web crawler can go and crawl different pages, right, we have to come up with some ideal rate at which these different web pages need to be crawled, right? So that's the idea, and that's what this optimization problem is trying to do, right? However, existing algorithms, okay, either presume the knowledge of the exact rate at which a web page changes, or they make use of offline estimation methods such as the MLE, okay, to estimate these page change rate, right? So in this talk, we will make use of the idea of stochastic approximation to come up with an online estimation method for determining the rate at which a web page changes. Okay. All right. So let me now discuss this research question in more detail, and I'll also try to give a pictorial description of what is happening. Okay. So the question that we are trying to discuss in this talk is to determine the rate at which a web page changes. Right. Okay. So you may wonder, oh, what is so hard about it? Well, the challenge is that we only get to know if the page has changed or not from the previous visit, but not the number of times the page may have changed, right? So let me illustrate or describe this using this figure. Okay, so let's imagine that this black line over here represents time. Okay, so this represents time. Okay, and these x's denote the times at which the web page changes. Okay, so this blue color corresponds to these x's where this web page changes. So note that there is only one web page at this point. Okay, so we would like to understand how frequently does this web page changes, right? And the first thing to keep in mind is that the times at which this web page changes is random, right? And in particular, you can see that the times between two successive changes is random, right? So so we would like to somehow figure out the average rate at which this web page changes, right? Now, what is this challenge, right? The challenge is that let's imagine that the red dot denotes the time at which we access this web page, right? So we access this web page at this time, then thereafter we access this web page at this time, thereafter we access this web page at this particular time, and so on, right? The challenge is that whenever we access, we only get to know if the page has changed or not with regards to the previous access time, right? So you can imagine this time when you visited the web page, or when the web crawler visited the web page at this time instance, okay, it may be downloaded, okay, the copy of the web page at this time, right? So after some time, which is denoted by the second red dot, it visits the web page again. In this time interval, you can see that the web page has changed 3 times, right? However, when you get to visit, or when you visit the web page at this time, you only get to know if the page has changed or not, but not the number of times the page may have changed, right? So one way you can imagine is you downloaded a copy here, you downloaded another copy here, right? So let's draw those 2 copies. Let's say these are the 2 copies, and you compare these 2 copies, right? So by comparing these 2 copies, you can determine whether this copy is different to this copy or not, right? So that's the only thing you can determine, but you won't be able to determine the number of times the web page may have changed in this interval of time. Okay, so under this challenge, we would like to estimate the rate at which the web page changes. So I hope the goal is clear. So whenever someone gives you this problem, right? So in my case, I had an opportunity to visit Professor Avrichan Constantin at Indria in France. So he is one of the experts in communications. So he gave me this problem, and whenever you are given such a problem, right? One of the first things you have to do is you have to mathematically model this problem, right? So in this case, we followed the following prescription. Okay, so what did we presume? We presume that the times at which the web page changes, which is denoted by sk over here, has the following property, right? So we presume that s0 is 0, right? And thereafter the interchange times, right, they are independent and identically distributed exponential random variables with some unknown rate delta, right? So if you go back over here, what we are presuming is that these time instances, right, 1, 2, 3, and so on, right? So this is, let's say this is S0, this is S1, right? This is S2, this is S3, this is S4. So what we are presuming is that S1 minus S0, S2 minus S1, S3 minus S2, and so on, right? All these random variables are identically distributed, they are independent, right? So I can say that these all random variables are independent and identically distributed random variables, and their distribution is exponential with some unknown parameter delta. Is this okay? So this is what we presume with regards to the times at which this web page changes. Okay, so that is what has been described over here. So apart from this, we presume that the web crawler accesses this web page at time instances denoted by tk. Again, we will presume that t0 is 0, right? And we also presume that the inter-access times, right, that is tk minus 1 for different values of k. Again, this sequence of random variables is independent and identically distributed, and the distribution now is again exponential, but with some known parameter p, right? So why is this known? This is known because the web crawler has to decide at what rate it has to access a particular web page, right? So web crawler knows this value of p. However, the web crawler may not know the value at which this web page changes. Okay, that is why this delta is unknown while this p is known. Okay, so going back to this figure, what we are presuming is that the inter-access times, right? So the inter-access times are basically the gaps between these red dots, right? So one is this, the other is this. So this is t1 minus t0, this is t2 minus t1, this is t3 minus t2, and so on. And we are presuming that these three random variables are independent and identically distributed, and the distribution is exponential with some known rate p. Is that okay? All right. Now, if you recall, I mentioned that there is some challenging aspect over here, which is that we don't get to know the number of changes that may have occurred between two successive accesses. Instead, we may only get to know if the page has changed or not. Okay, so this is denoted by this random variable ik over here, and the definition of ik is that this ik is a Bernoulli random variable, that is, it takes the value 1 or 0, and it takes the value 1 if the web page got modified in this time instance, right? tk minus 1 to tk. So recall that these two things denote the access times, right? So we are sort of looking at the inter-access time, and we are asking if this web page changed or not, right? And if the value of ik is 1 if the web page changed, and it is 0 otherwise, right? So now with this model in mind, we can state our formal research goal as follows. We would like to estimate the rate at which the web page changes, which is denoted by delta, but we have access only to the values of ik. Furthermore, the values of these random variables are revealed in a sequential fashion. So I hope it is clear what our research problem is given this model. Okay, so I'll maybe pause here for a second or two. If anyone has any questions with regards to the mathematical model as well as the research problem that we are looking at, this may be a good time. At the towards the end of my talk, I will sort of justify or provide a justification why this is a reasonable assumption to make. All right. So, are there any questions at this time? All right. So I don't see any raised hands. So maybe I can advance. All right. So here is our proposed algorithm. Okay. So this is our algorithm that my collaborators and I together formulated. So this is an algorithm that we have formulated, and hopefully by the end of this talk, you will be able to appreciate how we managed to come up with such an algorithm. Right. So what is the algorithm? Well, the algorithm is very, very simple. The first thing is to run this algorithm or to implement this algorithm, you need to provide it with some arbitrary initial value x0 and some step size sequence, right, which we denote by alpha n here, right? And the update rule for our algorithm at time tn plus 1 is denoted over here, right? So how would we go about executing this algorithm? Let's say someone gave us this x0, okay, which is denoted over here, right? So what we will do is we will obtain the value of I1, right? So I1 could either be 1 or 0 depending on whether the web page changed between T0 and T1, right? So we, as soon as we get this value, we will go about updating our value of x0 as follows, right? So we will go ahead and run this algorithm and get x1, right? So the key thing to note in mind over here is that x0 is known, alpha 0 is based on the step size sequence that we have chosen. The value of I1 gets revealed at time t1. So we know x0, we know p. Recall p corresponds to the rate at which the web crawler crawls this web page, right? So all this information is available to us, so we can execute this algorithm to obtain x1. So similarly, once we have x1, we can again rerun this algorithm to obtain x2 in the following way, right? So again, at time instance t2, okay, we will get the value of I2, which can again be either 1 or 0, right? And whatever that value is, we will accordingly use it or substitute it in this update rule to obtain the value of x2, right? And we will keep doing this, and the value of xn will keep getting updated, right? And our main result is the following, right? If the step sizes satisfy some relation of the following kind, right, then your xn will almost surely converge to delta, right? So let me go back to this algorithm. The first thing to keep in mind is that this algorithm is a stochastic algorithm, right? By stochastic, I mean that the values of these random variables I1, I2, I3 and so on, right, each time you try to run this algorithm, they will be different, right? And since they are different, and in particular they are random, the trajectory of these xn iterates, right? The trajectory of this xn iterates, this is also going to be stochastic, right? Nevertheless, what our main result says is that on almost every run, right, or with probability 1, as n becomes larger and larger, xn will converge to delta. Okay, so that's what this algorithm, that's the convergence guarantee that we can provide for this algorithm, right? So I would again like to emphasize that the significance of this algorithm is that it is only making use of this IN values. Recall that IN only tells us whether the page has changed or not between two successive visits, but it doesn't tell us anything about the number of times the web page may have changed, right? So despite that, by just making use of this value, right, we can actually estimate delta. Okay, so that is the prowess of this algorithm. So separately, our other main result also looks at the convergence rates of this algorithm. In particular, it says that if you choose a step size of the following kind, right, where alpha n is of the form 1 over n plus 1 to the power minus to the power alpha, right? Like for example, alpha 0 will be 1 over 1, alpha 1 will be 1 over 2 to the power alpha, alpha 2 will be 1 over 3 to the power alpha, and so on, right? So if you choose your step size in this fashion, and if you pick some alpha between 0 and 1, then we can guarantee that the rate at which xn goes to delta, right, this is of the order n to the power minus alpha. Okay, so that we can guarantee. So in this talk, I will focus on this aspect of our main result. In particular, I'll make use of the theory of stochastic approximation to briefly describe how one can guarantee that xn obtained via this algorithm almost surely converges to delta. Okay, all right. So let me go over some fundamental facts, right? So if you recall, these INs are 0, 1 random variables, right? And hence they are Bernoulli random variables, which in short I denote by Ber over here. And by making use of the independence and memoryless property of the exponential random variables, one can show that this IN sequence is independent and identically distributed Bernoulli random variable with parameter delta over P plus delta. So recall that delta corresponds to your web page change rate, right? Whereas your P corresponds to your access rate, right? So I'll sort of briefly tell you how one can show that these INs have this, this distribution, or in particular, the parameter of this Bernoulli distribution is this, right? So the brief idea is the following. Suppose n of AB denotes the number of times the web page changes in this interval AB, right? Now, using this independence and memoryless property, one can show that n of AB is actually a Poisson random variable with this parameter. Okay, so the parameter is delta tau, where delta is this expression, right, and tau is the length of the interval, right? So one can show this property. Now, using this property, one can figure out that the expected value of in, given that the inter-access times is tau, right? So one can use this fact over here, and one can figure out that this expression, okay, denotes this expression. So notice that expected value of in is a Bernoulli random variable. So Bernoulli random variable, this value will take 1, okay, only if the number of changes is at least 1, right? So from this relation and the fact that this is a Poisson random variable, one can see that this probability is actually 1 minus expected value, 1 minus e to the power minus delta tau. So using this expression and some iterative conditioning, right? So in, notice, depends on two things. One is the length of the interval and the value of in, right? So if you sort of use some iterative conditioning and do this expression, one can then see that expected value of in is actually delta over p plus delta, right? So I think I have 10 more minutes. Can one of you please confirm if I have 10 more minutes? Manoj? All right. So I'll presume I have roughly 10 more minutes. And
Yes,
I will
sir.
continue, right?
Yes.
Okay. Okay. So I'll just give a quick summary of how one goes about this algorithm, analyzing this algorithm. So recall that the update rule for our algorithm has this form, right? So how can one guess that such an update rule will do well, or in particular, get the job done, right? So to analyze any such algorithm, the key idea is to rewrite it in an appropriate way, right? So the idea is to rewrite this algorithm in the following way, right? And we have to suitably choose this h, and I will tell you how to choose this h very quickly. But at this point, I am saying that this algorithm can be rewritten in this form for h of x equal to this expression and mn plus 1 equal to whatever we have over here, okay, minus h of xn, right? So I hope it is easy to see that if you take h of xn and add mn plus 1 to it, since you have minus h of xn, this expression, okay, and this expression will cancel off, and in this expression you will be only left with this, which comes from this part over here, right? And by rewriting this, you can see that mn plus 1 has this form, right? So notice what we have in the round bracket. Okay, so what we have in the round bracket is in plus 1 minus delta over delta plus p, right? And in particular, this delta over delta plus p is the expected value. So in a sense, this round bracket is like a zero mean random variable. Okay, so this is very, very key, right? So in short, why did I choose to write this square bracket as h of xn plus mn plus 1, where h of x is this? Well, the simple answer is that I added and subtracted a suitable quantity so that mn plus 1 has this form where some expression is of a zero mean nature, right? So by ensuring or wanting to ensure that this is zero mean, one can figure out what one needs to add and subtract, right? So I will, in the next slide, elaborate what are the advantages of, having such an expression and having such an expression, right? But at this point, you can see that once we are able to write our update rule in this fashion, right? If you sort of look at how the dynamics evolves over m steps, right? So if you sort of use this update rule for m many steps, you can see that the value at n plus m plus 1 will be related to the value at time n in the following fashion, right? And keep in mind that I have used different colors for two terms over here, right? So I will claim that this is the cumulative noise, right? And this is an approximate solution of a suitable ODE, right? In some sense, you can imagine this to be the driving function, okay, which is driving the behavior of your xn, and this part that is over here in sense is some cumulative noise, right? So over the next two slides we will try to understand what is the behavior of this cumulative noise and what can we say about the behavior of this part, right? Okay, so what can we say about the cumulative noise? Well, let Fn denote the sigma field that is generated by these random variables. Okay, so x0 is your initial estimate, I1 is the value of this Bernoulli random variable, which is 0, 1. Similarly, you have I2 and all the way up till In. Right. So for those of you who don't know what a sigma algebra is, you can just imagine Fn to contain the information that is available until the time instance Tn, right? So you can think of Fn in some sense recording the information that we have until time information Tn, and it is not difficult to see that if I know the values of x0, I1 all the way up till In, then one can exactly determine what the value of xn is. Okay, so this notation over here tells that xn is measurable with respect to this sigma field, right? So because of this reason, right, one can show that this mn plus 1 sequence that I defined on the previous slide satisfies this property. That is, the conditional expectation of mn plus 1 with respect to this information is 0, right? So this actually follows from this this round bracket having expectation 0, right? So when I take the conditional expectation of this expression with Fn, the way to interpret is that this round bracket is a constant, and we are basically taking the expectation of this round bracket, and since the expectation of this is 0, okay, it follows that this expression is 0. From that, one can conclude that this sequence is actually a martingale difference sequence. In particular, if you sort of define Sn to be the sum of these individual terms alpha k mk plus 1, one can show that Sn is actually a martingale, and because it has some nice properties of the following kind, one can show that Sn is actually a converging martingale sequence, right? And hence the tail of a converging martingale sequence. So if you see, I sort of look at the sum of these terms from n to n plus 1. So this is the tail, right? So if you look at the tail of this converging sequence, this will go to 0. So if you go back over here, this blue part goes to 0, right? Because this expression over here in a sense resembles the tail of a converging sequence, right? And as you take n larger and larger, this expression goes to 0. Okay, so that is the first key observation. The next part is to understand this part over here. So as I said, this I'm claiming is an approximate solution of a suitable ODE. So let me sort of take 1 minute to elaborate why do I claim that. Okay, so consider this ODE x dot of t equals h of x of t. Okay, so one can imagine or one can easily see that this is a deterministic ODE. While the algorithm is stochastic, this is a deterministic ODE. And if I asked you, can you tell me something about the solution of this ODE which passes through some value x prime at time t naught, right? Then it is easy to see that the value of this solution at some time tn will be having a form like this, right? So it will be x prime plus integral from t0 to tn. Whatever we have over here, I have substituted. So basically this is saying something about the derivative of the solution. So if you integrate this, I hope you agree that you will get some expression like this. So if you put in some intermediate values between t0 and tn, let's say t1, t2, all the way up till tn minus 1 to tn, then I hope you agree that we can break this integral in this form, right? And if you denote alpha 0 to be the gap between t1 the gap between t0 to t1, alpha 1 to be the gap between t2 to t1, and so on, right? Then this sum can be approximately written as x prime plus alpha 0 times h of x0 plus dot 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 alpha n times h of xn, right? So this is referred to as the Euler approximation, right? So this is referred to as the Euler approximation to this solution, right? An Euler approximation to this solution that we have over here, right? So if you go back and see the expression that I had written before, okay, that is exactly this, and one can now see that this expression very closely resembles what we have over here. Hence, this expression can be viewed as a noisy Euler approximation to this solution, right? So in other words, this expression mimics the solution trajectory of this ODE that we have over here, right? So now one can use the theory of stochastic approximation to show that any update rule which looks like this, okay, that converges to a suitable invariant set, to a suitable invariant set of this ODE, right? And for the ODE that we have in our case, one can show that it has delta as its unique globally asymptotically stable equilibrium, right? So using the ODE theory, one can then say that the update rule that we have must satisfy this property that we have stated, right? So I'll take like two more slides and sort of give some empirical performance measure, empirical performance comparison of our proposed algorithm, right? So what we did was, in order to see if our algorithm is indeed capable of estimating the rate at which a web page changes, we actually took an arbitrary Wikipedia page, okay, which is called as template talk did you know, and we went there and figured out how many times did it change in this period, that is from April 1st 2020 to August 31st 2020, and we saw that this web page actually changed 4043 times, right? So using the times at which this web page changed, right, we somehow statistically estimated that the mean time to change, right, or the mean rate at which it changes must be this, right? So this is roughly calculated in terms of days. So roughly one change per, sorry, I don't know what is the unit. I think it is in minutes, I think, or maybe in hours. Okay, I have to check that. But in some unit, the rate at which this web page changes is actually 1.1098, right? So then what we did was, we looked at the times at which this web page changed and compared it with an exponential random variable with this rate, right? And we use something called as a quantile plot to verify our modeling assumption that the interchange times are exponential random variables, right? So we used a quantile plot to actually see if that modeling assumption is indeed correct, and we observed that we get a quantile plot of the following form. And for a quantile plot, if you get these points which are more or less on the 45-degree line, then one can say that indeed the modeling assumption that we have made is valid, right? So in such a situation, we went ahead and ran our algorithm, and so our algorithm only makes use of these I1, I2 and I3 and so on, these kind of values, right? So we ran our algorithm and this was the performance that we obtained, right? So you notice that there is a black line over here, okay? This is exactly the mean time at which it changed, right? And these are the different algorithms that we compared our algorithm against. In particular, this is the algorithm that we discussed in this talk, and this is the algorithm that is typically used, which is called as the maximum likelihood estimate. So in this plot, you can compare the green curve with that of the red curve, right? And you can see that we actually managed to obtain an estimate as quickly as the MLE estimator, right? So in this case, we chose P to be 0.5. So P 0.5 means, the rate at which the web page is also very large as compared to the times at which it changes, or the rate at which it changes. So notice that this is comparable to this, in which case we observe that all estimators more or less do a decent job. Okay, so then what we did was, we changed the value of P to 0.1. That is, we now access the web page at a slower rate. Okay, and in this case, we can see that the MLE estimator actually does a better job than the red estimator, right? So then what we did was, to this red estimator, we added something called as a momentum, right? And we obtained this purple estimator, right? So the momentum estimator is also very, very simple, right? And then we observe that once we add momentum to this, stochastic approximation estimator that we discussed, its performance again is comparable to that of the maximum likelihood estimator. Okay, so with this, maybe I'll stop and I'm happy to take questions. Thank you. Yeah, yeah.
Yeah, hello everyone. So if anybody has doubt, I will give you my mobile and you can ask directly in Google Meet to the sir. Okay. Anybody have doubt? Yeah. Hello. Anybody? Uh, okay. Okay. So nobody has any doubt. Okay. Okay, sir. Yeah. Hello, sir.
Yes.
Yeah. Probably. So,
Maybe they can
nobody has
contact me
any
offline.
doubt.
If they have
Yeah.
any interest.
You can.
Okay.
They can contact you. Right.
Via email. Okay.
Via
If they
email.
have
Okay.
any.
Okay. Can you show that email slide with or anywhere your contact is there?
I'll just go to the first slide. Okay. Maybe I'll just write it. I mean, they can search my name online and we can maybe very
Okay.
quickly
Okay. You
find
can.
it.
So everyone, you can search sir online and you can ask any doubt if you have.
All right. Okay.
Okay.
All right. Thank you.
Yeah. So can you provide the slides to the student, sir?
Yeah. Sure.
Okay. Okay. Sure. So share it with me, and I will share it with everyone.
Yeah, sure.
Okay. Thank you, sir. Yeah. Thank you, sir. Thank you for your time and your immense knowledge in your research, Jiva.
Thank you.
Yeah. Yes. You can sign up.
So, hi everyone. Good morning. Uh, I'm Sandamaran and I'm a data scientist at Robustness Center for Data Science and AI. So, thank you for the Paradox team for inviting me and giving me the opportunity. So, I'd like to talk about India Data Commons. It's a unified database for all of Indian data, and it is a project initiated by IIT Madras and it is supported by Google. So I'd like to start with what is data commons at the beginning. So, okay, so there is data commons and there is India data commons. So I'd start with what data commons is. Data commons is a platform, a website to be named. So it's a website where we are planning to have almost all the data that is available to the public. So we are gathering all the openly available public data and then we are making it available under one API. So that is the main motivation for data commons. Google started this project in 2017 in US. The US, the core team in Palo Alto, California is currently heading this project, and they started with doing this for US data. And once they finished their fair share of what they want to cover in US, they wanted to do a similar thing in India. So that's when they approached us, and we started this India Data Commons, which basically highlights the Indian part of the data. So we thought this is so like we have a website for data commons called datacommons.org, but we thought that India data is too rich and it is not getting properly highlighted in when it's along with the US thing. So we started a new platform called India Data Commons to like highlight the Indian part of the data. So that is the main motivation for starting this. And then I would like to explain why do we need data commons in the first place. So we are like hearing this term, right? Data is the new oil. Everyone is after data, and everyone is giving data. But like, and the data informs our understanding of so many issues. Like if we want to like see how public health or education or any key performance indicators in our nation is currently behaving, we have to look at data. Like we have to go and collect data and analyze this to get an understanding of what's happening at the moment. But pre-processing this data is laborious. It involves a lot of grunt work, and actually, frankly speaking, no one is ready to do that. And that's why a lot of raw data is in silos at the moment. So like people collect data and they host it somewhere in the hope that someone will take it and pre-process it and analyze it. But no one is actually ready to do the pre-processing step because it's tedious. So we are doing that for you. What we are doing is that going and collecting raw data, the raw publicly available data, and all the nooks and corners of internet, and we are pre-processing it and making it available through this data commons portal. And that is one of the main ideas, main objectives of this data commons efforts. I will come to that in a bit. But that is a good question, thank you. So, and this merging, pre-processing, so basically, if you want to do some cross-domain analysis, say if you want to like compare literacy rate of all the Indian districts and maybe like life expectancy, we had to go to like two different ministries. Like we had to go to Ministry of Education, we had to go to Ministry of Health and Family Welfare. We have to download two different data sets, and we have to find some common IDs to map it. And finding common IDs to map India data is really hard because we have a lot of spelling variations in the Indian administrative regions itself. Currently, we have something called local government directory, which is trying to like standardize the names and like having some IDs for it, but still it is still in the development. And if we look at the historic data, like data like before 10 years, there is a lot of spelling variations that don't add to what we are seeing now, and like merging this historic data is really hard. So we are also dealing with that so that no one else has to. And so as I said, pre-processing is very limiting. And so for example, if I am a domain expert who don't know how to code, or even if I don't know how to do Excel, but I have a lot of domain knowledge, and I can, if I have data and I have easy means to like analyze it, visualize it, and which means I can bring out some new insights that no one else can do. But I can't do it since pre-processing all this requires some kind of coding knowledge or even some kind of technical knowledge. So what we are doing is we are enabling the people who don't know programming or who don't have any technical knowledge to like use our platform and then gain insights, like mine out insights from the data that we are making it available. So these are the things that we are trying to achieve through making data commons public and openly accessible to everyone. So I'd like to explain how it works. I won't go into much technical deep into it, but I'll just show you overall view. So what we have is a single knowledge graph. So that's where your question comes in. So in data.gov.in, what we have is a lot of APIs. We call it as statistical variables in data commons context. We have like single statistical variables in multiple APIs. For example, we have an air quality index API for data commons, which gives us like air quality for like around 300 stations around India, and it is getting updated every 4 hours or something. So using the single API, we can keep on collecting data from it, but we have to compare it with some other like water quality or something. We have to go to like the water quality has multiple things, and we have like state-wise APIs from data.gov.in. So it is a lot of work to merge everything. We have to do some national level analysis. It's a lot of work to do in data.gov.in. So in data commons, so we are basically using a lot of data from data.gov.in. So that's where we get the data from, but we are getting it and like making it user friendly and more accessible to the public. If they want to do any kind of like analysis at any resolution, they can do it. If they want to do it national level, state level, district level, they can do it. So that's how we enable people. And we do this by having a single knowledge graph that comprises of all the entities, all the data points that we are taking in. So everything is connected to everything. That's why, that's how we enable this cross-domain analysis. Like there isn't much distance between going from one domain to another domain. We can easily traverse through it. We can easily compare data sets between like statistical variables between multiple domains like education, healthcare, agriculture, everything. And yeah, we do the pre-processing for you. They can, users can like aggregate anything, and the whole website is done in a very user-friendly way, so anyone can go ahead and start using it. And this is something new. So connecting everything to everything is new, because when we think of data platforms, what we see is like data sets arranged based on categories and ministries and so on like that. But this is something new, right? So what we do is we built a whole new file type that we call as MCF files, which is meta content framework files, and we build a parser ourselves, and then we are using this to enable us connecting these entities. So I'll just show you a simple example of how the entity information, the metadata is being stored. So what you see in the left is what we actually write in our schema. So we have something called TN, which is Tamil Nadu, and we have something called Chennai, and the DC ID is basically the Wikidata IDs for these platforms. And we have this type of parameter which says what kind of entity is that. Tamil Nadu is a state, Chennai is a district, and we are also saying like Chennai is contained in place called Tamil Nadu. So we are basically creating a link between Chennai and Tamil Nadu, and we are creating another entity called IIT Madras, and we are connecting IITM to Chennai using the same content in place. So this is a very basic example of how we are connecting data from different domains. So we are basically creating these parameters, like type of is a parameter that we created to define the type of a particular entity. So likely like we are creating parameters and nodes and properties that we need as we go, and we are making sure that everything is connected to everything, so that it's easy to like traverse from one node to another. So as I said, we are enabling non-programmers. So anyone who has domain knowledge or anyone who wants to like just visualize data, they can come to our platform and start using it and build visualization. So we have these three tools: Timeline Explorer, Scatterplot Explorer, and Map Explorer. So I'll just show you some examples here. So these are the plots that are generated from our platform itself. The first is the top one is the Timeline Explorer, where we are comparing like mean monthly wages between 6 different Indian states, and you can generate this graph with like 3 clicks from our Timeline Explorer. We just have to like select the states and select the parameter and select the type of chart, and you can generate this chart. And we have also Scatterplot Explorer, which compares 2 different statistical variables, and we also have Map Explorers, which gives you this choroplets, the map with color map information, which you can use to like compare across administrative regions in India. So apart from non-programmers, we are enabling programmers too. We have a lot of tools that programmers can use to like get easy access to our data. So we have REST API. Any data that you can see in data commons can be retrieved using our REST API. We also have a Python library, which is lightweight. Lightweight in the sense that the object you get is a JSON object or an XML object. We also have a heavier pandas library, where the object you get from the API, the library is basically a data frame object. So this is how it's basically a lightweight Python library, and we wrote a pandas wrapper around the lightweight Python library, where we can get it as a data frame. And we also have a Google Sheets add-on, so we can just go to Google Sheets and like you'll see some plugins in Google Sheets. We also have a data commons add-on, where we just can have a list of place names, and we can say that I need to get this data for these places from data commons. It will just populate the sheets like using this arrow. And we have some great data sets in our DB. So the data sets that you see on the left are actually what we have at the moment, and data sets that you are seeing on the right is basically will be available in a few months or so in the data commons platform. So yeah, thanks. That's it about it. So if you have any questions, so like this is a huge open source project. You don't have to be associated with any organization to contribute to it. We have a GitHub repository. You can just go ahead and keep on contributing to it. And I would like everyone to go and check our website datacommons.iitm.ac.in. It is a website for India Data Commons, and feel free to like play around the website and give us our thoughts on datacommons.rbcdsi.org. And I'd like to thank Professor Ravindran, who is heading the Robust Center, for guiding me, and this is a Google support project. Thank you. I'll be happy to take any questions. Yes.
In healthcare, do you have medical imaging data sets also?
Actually, no. So the main problem with our schema is we are only dealing with tabular data.
Okay.
So that is the issue, because we are still working on how to extend it to images, audios, the media information. But at the moment, our schema is not mature enough to involve imaging data.
Understood.
Are you also planning to do any sort of analytics on this data, or just a data collection and of course graphing, cleaning up exercise?
We are doing analytics, but we are doing only to show that what kind of analysis can be done using Algorithm, to like encourage other people to do some analysis.
No research goals on that?
No.
Okay. Thank you.
But we are encouraging people to do research.
So are you encouraging research goals through IITM or just?
No, it is open source project. Anyone can come and.
No, what I meant to say is IIT Madras sponsoring research on this data set through IIT Madras itself.
I don't think so, and yeah, I don't think so.
Thank you.
Which all domains these data commons are applicable?
So any domain, that's our USP, right? So we can get data from any domain as long as it's tabular data. The thing is, we need some kind of domain expertise to know how we can like create new entities and link it to the existing knowledge graph, right? So for example, we are dealing with air quality data at the moment. So we want to know what kind of things that people search. So like there is a beta feature that is going to come to this. So we can just ask data questions. Like we can ask how the air quality has changed in the last 10 years in Chennai.
Based on the data?
Yes, and it will give you a graph. But for this, we have to know how smart we are in creating this schema. And for that, we need domain expertise. But as long as we have that, we can add any data from any domain in data commons schema.
Okay.
How this is different from data.gov.in website?
I'm asking like there is another this website for data set called data.gov.in. So how this is different from that?
So in data.gov.in, there are APIs. There is like one API for each statistical variable, right? I gave an example of air quality data thing. But if you want to do some huge, like even in data.gov.in APIs are available only at a state level. There are very few APIs that are available for at a national level thing. So like it is really hard to like collect this data, merge it. Merging is a huge issue. We can't find common IDs from this data set. So like this will help you. So we are taking a lot of data from data.gov.in, but we are helping in merging the data set, pre-processing, and like easily create visualizations from the thing. We are enabling people to like skip all the. I mean, we're skipping the whole pre-processing step that data.gov.in data might like need. So that's how it's different. So all the data that we have is basically collected from the government published ministries. So we also have source for each data set that we are putting in. What we are doing is just like getting all the data from the government published sources and then merging it, making it available under the same API. We don't have to go to multiple places to like search for data.
Sir, so as you told you are working on maps.
Yeah, please.
As you told you are working on maps, do you also provide GeoJSON data? Because I find GeoJSON data very difficult. I have used some GeoJSON, but it gives distorted maps of India, like Jammu and Kashmir and so on. So you have shown us the map, and it is a correct representation of Indian map. So do you also provide GeoJSON maps?
So if you look at our GitHub repository,
Yes.
so we are taking these GeoJSONs from public available resources, and we have links for that in the GitHub
I
repository.
have found state level GeoJSON correctly, but in taluka level and in village level, it is some distortion in maps. Like Jammu and Kashmir was not shown as a part of India, so I can't use that maps in my projects as well. So do you provide those?
So you can get this district level data from India Data Commons GitHub.
And
repository.
when was it last updated?
So like there is a difference between what you see as India Data Commons and Data Commons.
Yes.
Data Commons doesn't has the same problem that you are mentioning because of the dispute. So like it is not about updating, it's about what we are using in the India Data Commons.
Have you seen Health Heat Map India website? It is also doing some similar work, and it is mixing 4 to 5 data sets from different domain and showing in a same map.
Which
So healthheatmapindia.com or .org, something like that.
I'm sorry, I'm not familiar.
Okay, but they are using some distorted maps, so I am unable to find it.
But the thing is, if everyone is publishing those maps, it is like reasonable to use those maps for analysis, right?
Okay, thank you.
So these government repositories like data.gov.in, they have a good process in place where the data gets collected right from the grassroots levels and gets approved. And there we can call them as living data, or they're regularly updated. What the process you have to see that this is your data also is updated and regularly refreshed?
So we do a data. We try to do a data.
Will that be useful for you?
I don't think so, because he's talking about web pages where we don't have all the information about it. But what we are dealing with is we have every information. We just have to go and collect it.
Okay, so either refreshes in, like, for example, data.gov.in will be structured. You will already know when the refresh. Okay, all right, thank you.
Any more questions from the audience?
Okay, we have time crunch. Sorry, if there are any doubts, please.
You can mail us.
Yeah, mail them. That would be a better. Okay. So after this, we are conducting. So flash talks will be there by other speakers for like about 15 minutes. So please stay back. Yeah, and Santamaran, thank you for your speech. Okay. Yeah. So I would like to invite Santamaran to on stage for the gift distribution. Yeah. Okay. Go now. Go and get it. Yeah. Please give him the gift. And yeah, I would like to Vrinda, please come on the stage and please, yeah, go. Okay. Yeah. Thank you. Now we have Miss Ananya Sai. She has completed her masters from IIT Madras, and currently she is a PhD scholar on dialogue evaluation system and metric at Rbcdsai. Please come on.
Hi everyone, I'll be talking about the automatic evaluation of text generation systems, and the dilemma I'm talking here about is you'll know as the talk progresses, but you'll get answers to why we are forced to have these automatic evaluation and why it is a challenging task, right? So let's get started. You might have heard the term NLG, which is natural language generation, and it refers to any software process that outputs a human understandable text in one or more languages. And there are several NLG models, or you can call them text generation systems, which have been proposed through these years, and they are of various types, starting from, say, something like rule-based systems or statistical models to what we have today, these RNNs, or right up to the recent transformers, including ChatGPT and models, right? So why is evaluation of these a harder task? Let's understand through a few examples. So one of the tasks is, say, machine translation, in the sense you're asking a machine to do so if you feed in a sentence in some other language and ask it to translate, now how does one evaluate the outputs given by the systems, right? Usually there will be a reference translation when you are looking at some benchmarks. Then here in this case it says the grapefruit is my most loved fruit, but the mango is her most, and the two outputs from different systems could be something like this. But as you can see here, one of them is way off, right? It's not even conveying the meaning, and the second one is right, but it uses slightly different lexical choices. This can be very different. So for example, if the task is something else, such as, say, question generation, where you'll give some context, which could be an image or a paragraph, and the task is to generate questions on that context. So now here, one reference that we have, for example, is that where was this photograph taken, which is a valid thing, but there could be an equally, there could be other valid questions that could be generated, right? So but then if a model outputs where is the motorbike, which has nothing to do with this, the relevance is lost, right? So there are these set of criteria. Which city is this? Probably it's not so answerable. Or if you ask how many passengers can fit, that might not need this context. It can be answerable directly. So there are these various set of challenges when it comes to evaluating any automatically outputted text, right? So for different NLG tasks, there are different lists of criteria. So in an ideal case, we want humans to evaluate these systems, where some expert human judges look at all the outputs and decide their score for each criteria, and maybe even an overall score. But this is not so scalable. It's very time consuming and expensive, and it is impractical to include in the model's training loop. What then is the practical way to evaluate NLG tasks? And the answer is automatic evaluation metrics. There are a bunch of options available to us today. I'll try to help understand an overview of these categories with some broad, at a broad level, right? So you can think of these as task agnostic metrics and task specific metrics. We'll start with word-based metrics. They look at direct word overlap or n-gram overlap between the reference and the candidate which has to be evaluated. And then it can look at the precision and recall of the matched n-grams between the two sentences. Or another word-based approach would be to use edit distance, where there is a reference and a candidate, and you want to see how many edit operations you have to do to go from the candidate to the reference. But then what about synonyms or paraphrases in these cases? They always get penalized in either of these approaches. So embedding based metrics come to the rescue, where you represent all the words numerically as vectors called word embeddings. Each word will have some vector associated, and the idea is that similar words will have their vectors closer in the embedding space. Say maybe ice cream and gelato, or extremely and very are very close. So you can instead match the embeddings rather than just the words. and there can be various heuristics to aggregate these word embeddings. The final thing that method I will talk about today is this trained metrics, which are the more recently emerging metrics. And one approach to do this training is to collect human scores on a database of references, and these candidate collected across multiple systems, and then you use this data to train a model, say maybe a neural network, to output similar scores. So yeah, now here there is a model which is, or a system which is trying to evaluate the outputs of other systems, right? And that completes this branch of task agnostic metrics. In task specific metrics, majorly where they also take the context into account, right? These are specific for each different NLG task, and these are all largely trained metrics as well. And yeah, the only difference is that along with the reference and hypothesis, they also take the context into account while scoring the output. Okay, now since I said these are popular and these are more recently emerging metrics, they have also been shown to be well correlated with human judgments. What does a good correlation look like? It's like this first plot over here, where as one of the so along x-axis you have the human score, and along the y-axis you have the model score, where if you instead use the human scores, these two change in a similar fashion. So if some two lists are well correlated, they have a neat diagonal that emerges something like this. But as you can see, with respect to these other word-based embeddings, they have a very flat line, very dissimilar from this. And Adam, which is a trained metric, has slightly better line of a diagonal, though it's not perfect. So anyway, as things progress, do you think these trained metrics would solve the problem and maybe replace the ideal human evaluations? Not necessarily. There are other caveats here. Mainly they are susceptible to these adversarial attacks. So if you take the case study of this Adam metric, which is a trained metric for dialogue evaluation, so it also takes context into account, then you can do back propagation by keep the parameters of the model fixed, and instead allow change in the embedding, right? So that way you can end up with an adversarial embedding which maximizes Adam's score despite being a bad sentence. So you can also look up a database of sentences, and where a human would give a very low score, but Adam ends up giving a high score. In this way, you can game these model-based metrics. So one potential approach towards a solution would be where we experimented with large-scale task-specific pre-training. In case of dialogue, it is this dialogue-specific pre-training, and we used Reddit corpus, which has 727 million conversations, and we also do fine-tuning with multiple references instead of having only a single reference. So we used the transformer-based model BERT. So this metric is called dialogue evaluation with BERT. And what about these adversarial cases that I was talking about? So we also use some of these for training. So by adversarial cases, I mean things where they vaguely look relevant, but if you take a closer look, they are irrelevant. The tricky part here is coming from the fact that these have some kind of either direct overlap or some indirect overlap with the context, as in meaning overlap with the context, but then yeah, they don't make logical sense as responses here. So if you train with these adversarial cases, even a small percentage of these adversarial cases exposed during training would help the model do better. Okay, so yeah, finally we were able to again show better correlations and also transferability to other data sets. Yeah, that's it. Thank you.
Hello. Thank you, Ananya Sai, for your speech. That was great. Now we have Mr. Sai Sarang. So he is right? Mr. Sai Sarangadas. He did his BTech in food technology at Anna University. After this, he was working with Perry Washington Company. Post this, he did MTech at IIT Guwahati. Currently, he is pursuing PhD at IIT Madras. Hello, welcome stage.
So my talk is on the effect of dormant spare capacity on the attack tolerance of complex networks. So basically, what's a network? A network has nodes and edges, and we are talking about deliberate attacks or failures here. And before going into the nitty-gritties of this work, so let's think about what let's assume that we are taking a road trip, and what would we typically do among other things is that first we will among other things we will check the tires, right? We'll check the robustness of the tires, and we'll use strong reliable tires so that we will have a safe journey. And additionally, we will also have a spare tire in the vehicle. So this concept is the core of our work. So what we do is to mitigate the effect of targeted attacks, we have spare capacity that's embedded within the system. So how we do it, in what way do we do it, that's guided by an algorithm, and let's see how it is. So basically, there are two types of algorithms to increase the robustness of a network. By robustness, I mean the network's robustness is said to increase when the size of the largest connected component. By largest connected component, I mean the component that remains connected after the network is attacked. The robustness of the network is said to increase if the largest connected component of the network increases. So one of the most talked about works in the in increasing robustness of network is the onion network methodology. What the authors did was basically they took a network, they will accept any change, they'll swap two edges between the nodes, and they will accept any change that will increase the robustness of the network. This formula here is basically the summation of the largest connected components as each node in the network is taken out. This is just a mathematical understanding. I'll give you a more intuitive understanding later. So this onion network algorithm is an example of an edge swapping algorithm. We swap the edges, and our algorithm is an edge addition algorithm. What we say is that we assume that we can add some edges in the on any given node, assuming that the amount of number of edges that we add does not increase over a threshold. And this spare capacity is like a spare tire in the car. It will not be activated till there is an attack in the system, only after which it will get activated. So let's look at the algorithm. So we take a network, we disrupt the network. So we take any centrality measure, and once that's happened, there will be two. Let's say there are the network now breaks down into a set of connected components. We take the largest connected components in the network, and we do certain things. So let me just illustrate this with an example. Let's assume that in a network these are the two largest connected components, and what our algorithm does is it will add an edge between every node pair in this network, in this largest connected component, and that edge which connects these two largest connected components and gives us the lowest sum of finite path lengths in the network, that will be the optimal edge. Why that is the optimal edge? Because if the edge that is connecting these two connected components has a lower path length, that means that we can traverse from one connected component to another, by traversing through a minimal set of edges. So that is why this is the most optimal edge. So for every potential edge between node pairs, we evaluate the sum of finite path lengths in the network, and that's saved in a matrix, and the optimal spare edge between these two connected components is the edge that has the lowest finite path length. Now, as I said, we do not allow the degree of a node to increase over a certain threshold. Let's assume that there's a power station and the node is a power station, and the edges are the transmission lines between the power station. We cannot increase the number of transmission lines over and above a certain degree, right? Because it doesn't make sense. It's not physically possible. So there is a threshold for this, which is called as a degree deviation. And if we perform this steps 1 to 5, iteratively, we can get the spare capacity for the entire network. So we break down the network, find the spare capacity, and build it again. So that's the core of our algorithm. So this is the intuitive meaning of a network. So this is the robustness graph, where the y-axis stands for the largest connected component in the network, and the y-axis stands for the number of nodes that have been disrupted as a proportion of the total number of nodes in the network. So this is the largest connected component of a network with added spare capacity, and this is the largest connected component of the network without the added spare capacity. So as you can see, the robustness is a measure of the area under the curve here, and as you can see, the one with one with the added spare capacity has higher robustness. Now what we did was we employed our algorithm to scale-free networks, Rbcdsi network, and the y-axis tells us about r by r naught minus 1, where r is the robustness of the network with the added spare capacity, and r naught is the robustness of the original network. And what we found out was, when betweenness we did for betweenness and degree centrality, we found that our algorithm was way better when compared with, to our knowledge, when compared with the existing algorithms as on date. So for example, the onion network methodology gives us a increase in robustness of around 150 to 200%, whereas ours is around 450% for degree. Degree centrality was used as a measure of node disruption. They also used it that in that way. So our algorithm is superior. Now we took certain real world networks. One is an air communication network, USR 97, and one is a power network, which is 1138 bus. And what we took these networks from network repository, and the average degree of these two networks, as you can see, is very divergent. And that's for a reason we wanted to find out how our algorithm behaves, how these systems behave when they are divergent. And as I said, degree deviation is a metric to limit the increase in the degree of a network of a node when we add spare capacity to it. Now same here. What we found out was, for both degree central, this is the increase in robustness value, and betweenness centrality was used as a measure of node disruption. And this is the one that was used for, this is the increase in robustness value when degree centrality was used as the measure for node disruption. What we found out was, for both these cases, the increase in robustness for 1138 bus with an average degree of around 1.3 is higher when compared to that of USR 97 with an average degree of 6.6. So what we thought was, because of the preponderance of edges for USR 97, we thought that it could the original network is so robust, or the new robustness value is not that high. So to check our hypothesis whether that is the case, we did certain things. You can go and see in the paper. So what is the cost of this spare capacity? What is the, let's take the 1138 bus for example, which is a power station. So basically the nodes here are the substations, and the edges here are the transmission lines between the substations. So let's say that we take out a hub in the network. A hub is a node which, let's say there is a very busy substation, and we take it out, which means that all the other substations which are giving traffic to this hub, which is the which is passing current through to this hub, these will be they will be rendered inoperational. So basically they will have this network will be able to will be used by our algorithm. So how it will be used? So if you think about it, so if this 1138 in this if this hub is destroyed, the downstream or the upstream parts of the substation which give the power to the substation, they are rendered inactive, and spare capacity can be added to it. In other words, we don't need to add spare capacity in terms of more substations. We just need to add spare transmission lines. So what happens is that disruption of 10 nodes in 1138 bus, there's a drop in the capacity utilization of those non-hub nodes, that is upstream of it, to 58%. So 42% of the substations that are in the network can be used to add spare capacity. Now, which means that the spare capacity can be added only for the transmission lines, and we don't need to create entire substations for it. So what is the capital cost of a spare transmission line? It's around 35% of the total cost of a substation, and if we add 5% of spare capacity in this network, the increase in project cost is around 2%, but there is a 530% increase in the network robustness, which is a benefit that is disproportionate to the cost. So this is the network that you can see, the 1138 bus. The blue lines represent the original network, and the red lines are the spare capacity that are added to the network. Now, what are the implications of this? So, see, we are not replacing one hub by the other. The problem with a network is that if you take out the hub, the network is rendered unoperational, right? So, we are not replacing one hub by another hub. We are distributing the spare capacity across the network. So, it's very easy for an attacker to identify a hub. However, it's very, very unlikely for him to know the entire map of the embedded spare capacity that is there in the network. So, the spare capacity is hiding in plain sight, and that gives some, a lot of robustness to the network. So, since there are non-biology students here also, so I will just skim through this. So, biological networks have a lot of, it's a cornucopia of spare capacity. There are a lot of concepts where the cell will, when perturbed, any cell when perturbed, will use the existing ingredients of the cell to get things right. So I am not going to go into a lot. I'll just tell about the first one. So basically, you all know about glucose, right? So in a cell, when there is no glucose, there are alternative sugars which can be used by the cell to metabolize and stay alive. And the cell will not, create an entire new metabolic machinery for it. It will just, make some small changes, one enzyme here, one enzyme there. It will predominantly use what's there. So this is the hallmark of spare capacity, the leveraging of existing potential, inactive dormant spare capacity. It's one of the hallmarks of biological networks. Others I'm just going to skip. So yeah, this we can talk about. So one of the problems of cancer is that it mutates, literally, but in the sense that it uses the spare, the concept of spare capacity is what makes cancer that is as deadly as it. In addition to drug efflux, target reactivation, and drug modification. I don't want to go into the technical aspects of this. So basically what happens is that there's a concept called, one of the concepts by which cancer cell survival is called as the adaptive kinome response. So what happens is that a kinase is an enzyme. So when one enzyme gets inactivated, there are other enzymes which are identical or similar to this enzyme, which will be used by the organism or the cancer cell to grow and mitigate the effect of the drug. So this is not only hallmarks of single enzymes, it's hallmarks of pathways, because like for example here there is a pathway called MEK-ERK12 pathway. So there are two different pathways, ERK12 and ERK5 pathway. And when this ERK12 pathway, which is a target for drug in colorectal cancer, when that gets attacked by a drug, this ERK5 pathway will compensate for it and keeps the cancer alive. So, and interestingly, ERK12 inhibits ERK5 pathway. When ERK12 pathway is alive, ERK5 is it stays dormant. In other words, the cell keeps the spare capacity dormant until it has trouble. So that's surprisingly similar to our algorithm. And yeah, thank you.
We have our Professor Ravindran sir here with us, who is heading our Robert Bird Center for Data Science AI. So on behalf of organizing committee, I request him to come to stage and give away the gifts to Sai Sarangdas and Ms. Ananya Sai. Please, sir. Thank you, Sai Sarandas. Once again, Ananya sir. Thank you, Ananya. Thank you, sir. We have two more speeches here. We have two more talks more. Mr. Virendra and Ritu for each 15 minutes. So I request you to stay back and hear that too.
Has a keen interest in data science. He holds a PhD in life and biomolecular science from the Open University UK and has conducted postdoctoral research at University of Vienna and the University of Copenhagen. Please come on stage, sir.
Right. So thank you for the introduction. So it's a short talk, so I will just try to give an overview and not go into details on one of the project we are conducting at our center. So the objective of this project is to analyze the risk assessment for the preterm birth in pregnant women. The main focus is the Indian population. So yeah, my talk is in 5 sections. I'll just try to give a motivation of what the project is all about, and I'll introduce the data and the data source and the methods we apply, results and conclusion, of course. So what is preterm birth and why it is important, right? So preterm birth is when a baby is born alive before 37 weeks of gestation. So at this point the baby is still fully developed and not ready for the outside world. So which means that there can be some downstream factors that can actually affect the mortality of the baby. So there are many causes for the preterm birth. So I've listed few of them. So infections in amniotic fluids or placental membrane can actually influence this. Existence of chronic conditions, so such as high blood pressure or diabetes can affect this. Nutrition, so both undernutrition and obesity could be one of the factors influencing the preterm birth. Lifestyle, so smoking and consumption of alcohol are also known to have an influence in this. And lastly, also genetics plays an important role here. So if we look into the number of preterm birth across different countries, we see India is almost ranking number 1 here. Yeah, of course, but you say that India is mostly populated and we see this, but if we look into the preterm birth rate, then actually India is doing worse than many of the developed countries, in that case also with China. And if you look into the number of death rates for the preterm birth complications, then India it records around 100 to 200 deaths for the preterm because of the preterm complication in every 100,000 cases, which is actually too high compared to the other developed countries also against China. So how can we reduce these numbers? So one way is by actually assessing the accurate gestational age. So in this figure, I'm just showing the whole timeline of the gestational age, starting from the last menstruation until the birth. So if the accurate gestational age is known, that can actually play a very important role with which the clinicians can take informed decision for the downstream the planning of the whole pregnancy treatment. So which can actually lead to a better outcome rather than the preterm. So the gestational age can be measured right in the first trimester as well as in second trimester onwards. However, if the pregnant woman if she decides to reach to the clinic in the first trimester, then the gestational age can be computed using the traditional LMP method, which is by asking the last known menstruation date, and the difference between the scan date and the menstruation date will give you the gestational age, which is actually full of bias because nobody actually remembers the last menstruation. So hence we have a more stringent, more accurate method, which is CRL based. So CRL is basically the length between the crown and the rump of the fetus captured in the ultrasound. So this is considered as the most precise way to actually compute the gestational age. So there are actually multiple formulas which have come up and which are being used worldwide. I'll come to that in a minute. So let's say just in case the pregnant woman decides to reach out to the clinician only in the second trimester, then we are missing out the whole CRL data completely. So there's no way that gestational age can be determined by the most accurate method, which is the CRL based. So in that case, in the meantime, the baby has grown. So there are many other phenotypic features that can be used. So yeah, here in the right side, you are seeing the ultrasound of the head, image of the head, abdomen, and the femur. So these are the measurements which are generally used, and these are also the measurements which are commonly captured across the clinics all around the world. So these can be used for the measurement of for actually prediction of the gestational age. So all is good. So one can do that, but what is the problem? So the problem is the way we are computing the gestational age. So here there's a formula called Hadlock, which was introduced in early 1990s, and it was developed with a very small cohort, consisting of very homogeneous population. That is only 392 Caucasian women, and also taken in only one center. Even though the formula is still being applied worldwide, so there are two variants of the formula. One is CRL based, where we have the CRL information so that we can compute the gestational age in the first trimester. But there's also the other variant where we compute the gestational age using the ultrasound features like head, femur, and abdomen perimeter. Yeah, but again, these formulas, the formula which is being used, which is the Hadlock formula, is again coming up from a very old data set from a very homogeneous population. So we believe applying this in Indian population, which is actually being done at the moment, is actually creating a lot of inaccurate prediction of gestational age, which further leads to the inaccurate measures taken throughout the course of pregnancy, and that can lead to the preterm birth and adverse cases in Indian population. So we want to change that. So that's where our Indian cohort comes into picture, called Garbini. So it is funded by DBT, and it is executed by THSTI Faridabad. So it was launched in 2015. It's a longitudinal cohort, so different kind of data is being collected at different time points, and more than 10,000 women are enrolled in the cohort, and various kind of features are recorded, such as ultrasound characteristics, clinical characteristics, socio-demographic characteristics, and so on. So we have a very rich data set to work with, so which we can now use to compute the gestational age for the Indian population. So this is the prediction for the gestational age in the first trimester. We call it as so I'm not going to talk in detail about this because this is already out and tested, and we call it as Garbini GA1, and we have developed a polynomial regression formula which is able to compute the gestational age comparable to the other formulas which are out there, but it is also sensitive and balanced, have balanced accuracy in classifying PTB in the Indian population. So I'm not going to detail in this. So what the other major challenge which we face is that in low and middle income companies like countries like India itself, more than 40%. So it is assumed it is more than 40% of women actually visit to the hospital only very late in their second trimester. So in that means there is no CRL data available, which means the most accurate way to find the gestation, compute the gestation age is not available. So one can only use the other ultrasound features, which we will be using as well. So before coming to that, here's just a workflow. So of the method we are applying here. So we have taken around 6,498 cases of pregnancy, which were found good to be used in the analysis, and we did some EDA and filtered some of the data right away. And then we ended up with 4,768 cases. We split that into, of course, test and training set. In the training set, we again further removed some outliers and used that for training. So we used different machine learning techniques. So I think I don't have to give introduction to random forest and gradient boosting to this audience. So they both are ensemble methods with slightly different way of aggregating the trees. However, genetic algorithm is not very common, I think. So it's a optimization technique, and it is rather general. So it's not only applicable through machine learning, but it is also applicable to simulation and other areas. So it is inspired by the natural selection. So I'll just give a brief introduction to that. So what it does is that suppose so it assumes that a given individual is a mixture of a few features. So the features which I talked about previously is the ultrasound features, right? So the measurements of head and abdomen and femur. So it considers that as individual, and given that following the analogy of the natural selection, it produces the population, and in doing that it performs the crossover and mutation, and it before every generation it tries to find the best performing feature. So in context to genetic algorithm, it will be actually computing the fitness function. So what it tries to do is with every generation it tries to come up with the best performing feature in order to compute the gestational age. So it tries to reach to the global maxima, but it's not guaranteed that it always reaches the global maxima. So it's generally recommended that whenever you apply this algorithm, you do it for multiple iterations and go with the results that are consistent across the iterations. So keeping that in mind, we went through the feature selection process. So we had multiple features, as I spoke about in our data collection. We applied the Baruta algorithm. It basically tries, it performs a Z-score analysis. It creates random features of the original feature called shadow features, and then it tries to find the importance for that compared to the random features in every iteration. And the ones which stand out are confirmed as the important features. So we can see that the 5 ultrasound features stand out significantly compared to all other features. And these are the 5 measurements which are commonly used across, commonly collected across most of the clinics all around. So that's why we thought to stick around with that, and go ahead with our modeling. So we started, so we took our 5 features. We also transformed them. We computed their logarithmic and square root forms. We also included them in the training, and we did the grid search for hyperparameter tuning. So we used range R for random forest and XGBoost package in R for the gradient boosting. For the genetic algorithm, we took a slightly different approach. So here we created multiple input sets of the features, the 15 features. And we used the leave one out approach, so that we had multiple input sets. This was done to find out whether particular feature is majorly, playing the important role in the determination of gestational age. we also for this we use the GA polyfit N package from MATLAB. So we generated the functions as such. There were 2, 3, or 4 terms. So 1, 2, and 3 here. 4 terms in the formula, and we also set a range of powers to each of the terms, 0 to 3, and we computed the GA in log. So because this was the standard way, the other formulas are published. So right into the results. So in here we are seeing in the x-axis the error in week. On the y-axis, these are the different formulas which we came up. So through the genetic algorithm, and also random forest gradient boosting is there, and some of the already published formulas such as Hadlock and intergrowth. So we see gradient boosting and random forest is performing very well in our test set, but we also wanted to check this using an completely independent cohort. So we used a independent cohort from CMC Vellore, and we collected a similar data set, and we applied our models to this. And what we see here is that random forest and gradient boosting, they terribly overfit, so they underperform here. It is not very surprising given the data we have is it has only few features which are being used, and it is expected. I mean, it's not very surprising to see the overfit. But what is interesting to see is the genetic algorithm, on the other hand, they actually perform consistently in the test set and the set from the completely independent data, which is from the which we call it as validation set, coming from the CMC Vellore cohort. So from these we took the top 5 formulas, and we actually reached out to clinicians, and we discussed about the formula and the features which are included in the formula, and we took their inputs, and we selected one of the formula as the GA2. And this was I'm not going to point out the formula, is still going to come out. So however, the valuable input from the clinician was that capturing the abdominal parameter, which is also there in one of the published formula, is very skill based. So it can go wrong, because also the boundary of the abdominal parameter, if you saw in the image I showed in previous slides, it is not very clear. It's very hazy. So it's skill based, and it can vary. And keeping that in mind, we excluded abdominal parameter from our formulas, which were actually one of the top 3, and we went with the other, which performed well. And we call it as GA2. Again, in this figure, I'm just showing its comparison against the intergrowth and Hadlock. Intergrowth is another formula out there using a mixed population, where Indian population was also included. So if we see the error rates in test and validation, error in weeks in test and validation on the y-axis here, our formula actually performs consistently better. And also in terms of RMSE, I'm not shown it here, but the RMSE is low compared to the other 2. Next, we compare our formula against the gold standard. So just to let you know what is gold standard. So we have the second and third trimester scan date. We also have first trimester scan date in our cohort, and this is using the test set, Garbini test set. So when we make the difference of it, we get n number of weeks, so t weeks. And again, at the same time, we can use the first trimester scan date and apply our CRL formula, which was Garbini GA1, which is already published, and come up with the gestational age for first trimester. And when we add the t weeks to this, we get the gold standard. So now the gold standard is obviously, we believe that it's the most nearest to the truth. And we compared all our formulas and the formula that are already published against the gold standard. And here we look into the preterm birth rate. So here we see that Garbini GA2, our best performing formula generated using genetic algorithm, performs better than far better than the Hadlock, which is actually in practice. However, intergrowth and GA2 doesn't have a very strong difference, which is expected because intergrowth also have Indian population in their study. So here the main aim of our project is to probably discontinue headlock, which is being used widely in India. One more plot here. We are in this quadrant plot. We are looking into the birth rate again. On the x-axis is the GA predicted through our formula, intergrowth and headlock, and on the y-axis is the gold standard. And we see the agreement in green and red, so either preterm and full term. And in yellow we see the disagreements between the gold standard and our formula, or the formula that are published, yellow and blue. And we see we have less number of such cases in our formula compared to the other two. Yeah, with that I would like to conclude. So here we actually offer a Gabani GA2 model which can accurately predict and easily applicable throughout the clinical measures in India. I say easily because these are only the 5 most commonly captured ultrasound features. So, and yeah, of course, further comprehensive validation is required, given that the CMC valor was a very independent cohort. Similarly, we have to also look for the other bigger cohorts where which can be actually representing the different socio-demographic classes in India. And its application is expected to benefit the clinicians, epidemiologists and the biologists, because they can make a informed decision in the course of their treatment in the pregnancies. With that, I would like to thank everyone involved in the project, Dr. Shinjini Bhatnagar, Dr. Ram and Dr. Himanshu Sinha, who are the pillars of this project, and everyone involved, all the students out there. Thank you so much, and thanks to you for the attention. Any questions? Yeah, so this is obviously not going to be very straightforward because it has to pass through many managements. However, the easier part, which is that the 5 features which we have collected or which we have used in our model are usually collected throughout the across all the clinics. So it's that's why it's applicable across the clinics. I actually cannot. Yeah. Yes. But not very near to the future, but yeah, as I said, we need a comprehensive validation using a broader cohort, pan-India cohort. So it should represent the whole Indian population, and then it will be suitable. We hope so.
So thank you for your time. Okay, now I want to introduce Mr. Rituraj Banwal. He has completed his BTech in Electrical Engineering from IIT Hyderabad and was previously working at Yahoo Japan as a software engineer. He is currently working on reinforcement learning under the guidance of Professor Nirav Bhatt and Professor Balaraman Ravindran. So please come on the stage.
So firstly, I would like to, I highly appreciate that you all waited for the last talk. And let me start with this talk. So I will be presenting transfer learning across heterogeneous agents. Before I move ahead, I would like to acknowledge whom I have worked on this project. So consider the case where you are trying to learn to drive. Now in this case, the instructor often actually provides you feedback, either explaining you what components are there in the vehicle, or most of the time it is actually easier to show than to explain things. So in this presentation, we'll be focusing on how do we learn from demonstrations by the instructor. So instructor often provides you the feedback in the process of demonstrating the process rather than explaining it. Okay, so the task is, given the instructor's demonstration, the learner tries to mimic the behavior of the instructor. Here the instructor in our case is a human being and the learner can be a computer agent. So the task is, for a given particular task, the instructor gives you a demonstration and the learner tries to mimic the behavior. Okay, so what is the demonstration in this case? So before I move further, so how do instructor actually takes action there? It observes the object, observes the robot. Say the observation that instructor makes is X, and the action that it takes, say for example, the action can be move forward, take a left turn, slow down a bit. All these possible action that instructor can take on the robot is the actions U. So based on the state, the instructor takes an action U. So, and once this action is executed, the robot moves to a next state, xt plus 1. Okay, so the demonstration can be actually be considered as a tuple where x is this current state and u is the action that the instructor took on that particular state x. And if we collect all these time step, state and action pair, it forms our demonstration. Okay, so how do we mimic the behavior? How do the learner will mimic the behavior? The most simple and yet very powerful algorithm, which is generally referred as behavior cloning, can simply be described as you actually take a function approximator f, which can be a neural network or any form of function approximator, which takes the current state x and tries to predict the output u hat. And you minimize the objective function either by mean squared error. So this is a very simple algorithm, and this will actually try to mimic the behavior of the expert, behavior of the instructor in this case. Now, in this learning from demonstration, we make a very strong assumption that the instructor is providing the demonstration on a same robot where the learner is trying to mimic. If we take the old car driving example, the car that the learner is trying to learn and the instructor is also providing the demonstration on the same car. So the agent that the system that is being used is both same in both the instructor's demonstration part and the learner's mimicking part. But what if the instructor's demonstration is on a wheeled robot, say in this case wheeled robot, and the learner is trying to mimic its behavior in a legged robot? Well, the same behavior cloning algorithm will work. Now, in general, it will not work because the same action is not leading to the same next state. Say both the robot is in the same state, and if you execute the same action, it will lead to a different next state, and hence the task will not be completed by the legged robot or the mimicking robot. So what if in this case, if you have a fast moving robot and a very slow moving robot is trying to mimic the same demonstration? Similar problems occurs here too. Since the same action doesn't lead to the same next state, the task will not be the slow robot will not be able to complete this task. In this case, where we have a robot which is actually a new perfect robot, and because of some wear and tear by time, the mimicking robot will not be able to mimic that behavior. So we can see that this task of learning from the demonstration, generally demonstrations are available by the instructor or from a different agent or from a different robot, and you want to learn the behavior in a different system, which is not entirely different but close approximation of the same system. So what if we can actually learn from the different demonstrations provided by different robot? It will help us utilize the demonstrations that are already available. We can use it better. Think in terms of the YouTube videos have so many videos trying to demonstrate the task that you want to do, and we can use those demonstrations to learn those behavior better. So now consider this task where we have two robot, a perfect robot and an older version robot, a wear and tear robot. To complete a same task, the instructor robot, the XI that is being referred on the left side, it takes xi, at the state xi, it takes ui to complete the task. And for the older robot, at the state xl, it takes action ul to complete the task. In general, we can say that depending upon wear and tear, how much old it has become, but in general, we can safely say ui will not be equal to ul, because both the robot have a different dynamics now. But the key observation is that to complete this task, we will actually be making the state sequences that both the robot will see will be approximately the same, because they will be completing the same task. So the key observation is that for completing the task, the state sequences may almost remain the same. Okay, so this brings us to the new form of our algorithm, which is called learning from observation. Here we have two different functions. The first function is the action prediction function, which is very similar to the behavior cloning algorithm that we first dealt with, in which it takes the current state and predicts the action. And then we execute this action on the robot. Once this action is executed, the robot moves to a next state, and this next state where the robot moves to, we will actually try to minimize the distance between this next state and the demonstrated next state. And then simply we will backpropagate the loss to update the action function and the state matching function. This is a very simple idea, and based on this idea, there are some of the experiments that we done on the simulation, where they consider this example of cheetah. This is a half cheetah though, in which the instructions were provided by the half cheetah how to run, what what actions should we take, and the imitator, the learner part, has actually a back foot of the cheetah on the right hand side is broken, and the mass is twice the mass. So just by looking at the imitator's demonstration, the back foot broken and twice the mass cheetah is still able to learn, which the behavior cloning algorithm will completely will not be able to learn, move the cheetah. Similarly, if you broke the front foot of the imitator robot and increase the mass twice, it shows that it can still imitate the behavior. There are many more examples on this website. Due to the time constraint, please visit this website. And thanks again.
Thank you, Ritu. So we request Professor Ravindran sir to come on stage to give the gifts to our speakers. Dr. Virendra, please come on stage. Thank you, Dr. Virendra. Next, we have Ritraj Banwal. Thank you, Ritraj. Thank you, sir. Thanks all for attending the session. Thank you so much.